All right, thank you. And thanks for joining. I know this is a difficult time for people, so thanks for taking the time to attend the talk. A little bit about Groq, since it's a new company. We literally just emerged from stealth only a few months ago, but we were founded in 2016. Seems like a good year to have minted a new company. We are located in Mountain View, California, and it was founded by a bunch of Googlers. Jonathan Ross was one of the inspirational initial people on the Google TPU project. And we're excited to be kind of shipping our first A0 silicon, our first product of what we call our tensor streaming processor. So this talk today is going to be kind of an architectural overview of that, and hopefully provide you some background on a little bit as to the motivation and what we're hoping to accomplish. So computer architects have been using these large dies now for the last 20 years, increasingly building complex microprocessors to exploit ever-increasing levels of instruction-level parallelism, and really growing these dynamic execution techniques, speculative execution, branch predictors, all of which add a lot of additional control logic and complexity. And unfortunately, these have been somewhat weaponized over the last several years. In particular, there's a nice article from IEEE Micro from a year ago talking about Spectre and Meltdown, and more recently, Zombie Load, that weaponized these vulnerabilities. And what we did is we took a different approach, and we started with kind of a broadly speaking, the approach we're trying to do is extract as much computational density that is measured in the number of deep learning ops per floor tile in the data center. And this in turn really drives the technology decisions that we made along the way in terms of the number of floating point and integer units that we can plop down. As I'll discuss, it's fairly inexpensive to drop down some floating point units or integer ALUs. It's difficult to keep them fed at full bandwidth. And so part of the trade-offs here is that we were hyper-focused on batch size 1, and that drives a lot of the implementation goals around memory bandwidth and some of the implementation decisions as well. So what I'm hoping to get across today is really the Groq chips goals were to focus on uncompromised peak performance. So we were looking for really providing as much computational density and focusing on batch size 1 workloads. And then to be able to provide a solution that provides both integer and floating point numerics on a single chip solution, so that if you're using this to deploy models or train models, you have a single chip solution that you can use for either inference or training. Our initial focus is on inference, just out of pragmatism, but the chip itself is capable of both. And then lastly is predictable performance, and that is how do we use determinism to be able to develop a software stack around this and to be able to extract good performance. So to start with this as an example, I'll use a conventional many-core processor that kind of starts as this homogeneous 2D mesh of processor cores. And each of these processor cores look effectively like this kind of homogeneous core where they've got a load store unit for interacting with memory system. They've got a floating point unit, an integer unit, and then they've got some instruction dispatch and control logic. And then of course they have some network interface for communicating between cores and off chips. And what we've kind of done is we've taken this organization and thought about it orthogonally a little bit, and that we've reorganized this tile architecture to reorganize it in 2 different dimensions. Along the row dimension, we've taken what would ordinarily have been these homogeneous cores, and we've distributed them so that a single row has all the constituent elements of a core. So for example, along a given row, we have a floating point, we've got integer ALUs, we've got memory storage for operand retrieval and storage. And along the vertical or in the column dimension, we've got a SIMD organization. So you can think of this as kind of restructuring our approach. And most importantly, what we've done is we've removed this intermediate memory stage from what is a common 5-stage canonical pipeline design. What that allows us to do is decouple the memory access the operands from the execution of those operands on the functional units. Or more precisely, we're removing the C from the CPU, and that is we're removing the centralized component of this, disaggregating the functional units across the chip to take advantage of this spatial architecture. So what this does is it interleaves our memory units and our functional units in a way that allows us to take advantage of data flow locality as it flows across the chip. Each of the tiles itself is computing a 16-way computation in a SIMD manner, and we take those and we produce 16 elements at a time in a 20-stage pipeline to produce 20 times 16 or a 320 element maximum vector length. So again, this is the basic idea behind the architecture is built on this concept of a deterministic instruction execution. We have a superlane that is one of these rows within the tiled architecture, and that allows us to take advantage of data flow locality. So as tensors are, for example, computed, we literally set up kind of a data tensor pipeline, so to speak. And as the tensors flow across the chip, we pick them up in the different functional units, we operate on the tensors, and we put them down back into what we call a streams. The streams act as a conduit. And streams registers are similar to your normal general purpose registers that you're used to. For example, if you're used to a traditional conventional CPU, where you do a load into a general purpose register, say for example, a load into register 3, and you can come back a week from now and that data that you loaded will still be in register 3. And that's because that data is static. This is different in that when you do a vector load into a stream register, it literally starts flowing east or west onto the chip. So we take advantage of this data flow locality to opportunistically use that and operate on the tensor as it makes its way from its source, i.e. from memory, all the way to the functional unit on which it's operating. So as an example of this, we can load a tensor from memory at time 1, at time 2, as it crosses past our vector processing unit, we take it and we can add some positive bias to that tensor, for example, and then it continues to flow on through what we call the SXM, or the switch execution module. And that switching module is part of the on-chip network that allows vertical data flow. It allows us to rearrange elements within the vector. And then lastly, we take that and we install those weights into one of our deep learning matrix units. And that matrix unit is what's producing your output features, which can then be the results that flow back at time 5 here get written back out to memory. So you can see how this contrasts from a conventional CPU where you're doing a load from DRAM and you're moving it from DRAM to the last level cache, and then from the last level cache to the next level cache. From there, finally, you make 3 or 4 implicit moves to get it into your general purpose registers where you can then do something and hope that it doesn't get a cache eviction. So what we had to do in order to provide the software-hardware interfaces to expose a lot of architecturally visible state to give the compiler complete control over the underlying hardware. And in particular, we expose a 320-lane programming abstraction built upon this concept of a superlane. And these superlanes are, as I mentioned, 16-way SIMD units that operate in a synchronization-free manner with the 20 superlanes on the chip. Each superlane has 144 independent instruction queues. That's across the entire chip. These instruction queues that are feeding the superlane go across all 20 superlanes. So you can think of this as program visible state, as we have the compiler generating 144 independent instruction queues, and those instruction streams interact with each other using these logical stream registers. And we've got a total of 64 stream registers that are 32 streams going east and 32 streams going west. So very similar to R0 to R31 in a conventional microprocessor, we just have S0 to S31, stream 0 to stream 31 different registers. And again, those are moving. So when you load something to them, they're literally moving the data along the data path. And then lastly this provides a total of 220 megabytes of on-chip memory. And that provides us a nice atomic unit by which we can not only fit common models like ResNet comfortably fits on there, what it also allows us to do is a building block for being able to scale out and build multi-chip versions of this so that we can do model parallelism across them. So what is data flow parallelism? Data flow parallelism, determinism is the concept of, imagine this thought experiment where you wake up in the morning and your commute and you just pick a ticket from an oracle and it tells you what time you have to leave home in order to arrive at your destination at exactly the right time. This concept of perfectly scheduled determinism is what the hardware seeks to execute. In particular, the hardware has no ability, there's no control flow, there's no hardware interlocks, there's no reactive components like arbiters or replay mechanisms that would perturb or permute the ordering of events. So what it allows us to do is it allows the compiler, it literally puts in the compiler's hands explicit control over all the orderings as they happen in the chip. So if we just come back to our example in a little more detail, we can see how this superlane organization is carried out as instructions are executed in a pipeline fashion over the span of 20 cycles, and that's how this 320 element vector is built up. So one thing that's central to the chip is tremendous amount of on-chip memory bandwidth. So if you look at the organization of the chip, memory is composed of two hemispheres, an east and a west hemisphere, and this is just mirrored right about the center of the chip. So there's a lot of symmetry on the chip and a lot of parallelism. Each memory hemisphere provides 88 banks worth of concurrency. So you can look at the memory system as being a very highly concurrent 176 bank, 176 way parallel memory system. And the SRAM, the on-chip SRAM bandwidth is about 60 terabytes per second. And that's what we use to be able to drive these large functional units that are doing a lot of the heavy lifting for the deep learning workloads. So as I mentioned, each MXM unit, or matrix execution module, the matrix unit is the functional unit that's doing a lot of the heavy lifting. And just to put in perspective here, we're able to load these 400,000 weights on the chip. We're able to load all 400,000 weights, do a matmul, and get the result back in about 80 nanoseconds. So that's less time than it typically takes to do a DRAM load, for example, and get the cache line in your last level cache. So what this fundamentally does for us is it allows us to provide a computationally dense substrate for deep learning workloads. And that is more than 1 teraopt per second per square millimeter. So this is a big chip. It's a reticle size 14 nanometer chip. And you can see around the outside of the chip is ringed with C2C modules. Those C2C modules are chip-to-chip links. There's a total of 16 chip-to-chip links that allow us to build high-radix networks to be able to scale out this approach. We'll be able to interconnect in a glueless manner multiprocessor support for a multiple tensor streaming processor system. A quick snapshot of what the instruction set looks like. Naturally, as I mentioned, this is a domain-specific architecture, so it has instructions that exploit tensors, and tensor is a fundamental abstraction on which the hardware is built. So the 6 different functional units are split out according to their type. For example, we have a memory unit that just executes memory instructions, loads and stores, gathers and scatters. And it doesn't do, for example, it doesn't do vector operations or matrix operations. It just does its component. And the same thing is true for vector operations. So we've got a vector processor that supports typical unary and binary operations that add, subtract, multiply, to those sorts of things, as well as conversions of from one type to another. The hardware natively supports both int8 and half precision in the matrix units, as well as FP32 in the vector units and int32 in the vector units. And lastly, the SXM is our switch unit that provides lane shifting capabilities, permutations of vectors, as well as sending and receiving vectors across the multi-chip interface. So just to give an example of what this staggered execution looks like, and to be very concrete, what it allows us to do is to support a stream programming model that's built on this producer-consumer stream programming, where we are taking tensors, reading them from memory, and sending them toward our functional unit, where they get operated on and produce an intermediate result that can be written back to memory, for example, or it can be streamed. So we can literally take these operations and chain them together in a way that doesn't even have to touch memory. So we're able to take the results and stream them back through ALUs to do, for example, dequantization or normalization on a layer-by-layer basis, for example. So what this looks like then is the chip is basically a big two-dimensional scheduling problem where you've got spatial and timing relationships that are being scheduled onto the chip. And so to give an example of this, I take the max pool layer from ResNet, and you can see that the arrows here represent effectively operands flowing between the functional units. And what happens is as time progresses from top to bottom here, you can see that the functional units are sending vectors back and forth across them, and this is how they exchange data, and it's a very straightforward way. The memory system provides the necessary concurrency to be able to support multiple operations simultaneously. So in this example, does a ResNet 50, which is doing a pooling operation as well as a Stride 2 downsampling of the input tensor to produce an output tensor that's half the size in both its horizontal and vertical dimensions. So like I said, I mentioned on top of this is we have our programming models, in particular, the programming models that have driven the last decade and a half of internet scale and distributed memory applications were built around, for example, reliable distributed memory communication through MapReduce, for example, as a good example of a distributed memory model. We build on those same models like MapReduce or MPI to allow scaling across, weak scaling across the nodes, but also within the context of multiple tensor streaming processors, we use a partitioned global address space to do strong scaling across multiple chips. So the streaming programming model is central to this to allow us to have a reasonable way of reasoning about correctness of programs, and the streams provide the conduit through which the functional slices interact. And this really evolves into two different things. We have complexity that arises on the chip, and we have complexity that arises as we scale multiple chips. And one of the things that the architecture does is it seeks to simplify and eliminate tail latency, and through a number of techniques that we use to maintain this deterministic execution, not only on the same chip, but across chips. So we maintain this notion of a globally synchronous operating environment across even multiple chips. So we look at the roofline diagram as a way to characterize our performance. It provides really some insight into two different operating regimes. The first one is the slanted area here where our memory performance is what limits our ability to execute. And so we are bound by our memory bandwidth. And in this operating regime, you can see that the slope of this line here essentially describes our memory bandwidth. The other regime is once we can load the operands, once we've loaded the operands to saturate the ALUs, we are operating into a regime where we are literally bound entirely by arithmetic performance. So that's really kind of the nuts and bolts of this. Is we want to see that, number one, we can support these two operating regimes. This is that we are able to drive at full bandwidth and extract as much value as we can from the underlying, effectively, the underlying transistors. As just a nice way to pop up and take a look at what this means from a performance standpoint, I wanted to share some of the ResNet 50 inference results. And these are for, you can see the Groq chip is up in the upper right corner here. This is a log-log scale with latency on the y-axis and throughput on the x-axis. So this is showing the characteristic latency throughput trade-offs as we make trade-offs about our batch size. So we can see that having a batch greater than 1 really does imply a trade-off between performance, latency, and throughput. And extracting good throughput and utilization sometimes requires that batch be used. Groq takes a very different approach in that we are targeting batch size 1. We want to have very efficient and low latency performance at batch size 1. You can take advantage of batch if you want to provide some weak scaling, but it doesn't require it in order to get good performance. And lastly, I wanted to walk through the software stack real quick because, well, frankly, these aren't any good without a software stack to drive them. So at the center of all this is the Groq software stack. And again, the idea here is to really expose as much computational density as we can to extract as much value from our transistors. And if we just kind of normalize that and look at what kind of performance we get from every transistor, or if you want to look at it as performance per unit of area, we get about 30,000 operations per second from every transistor, okay? So if you just kind of look at that, that's literally about a 6x or 7x performance difference compared to our closest competition. And we're able to turn that structured design, simpler compute into a better value for our end customer. So again, we're really focused on that uncompromised peak performance, both integer and floating point numerics in a single chip solution, and that predictable performance through determinism. We're able to control all of this deterministically through the compiler, and it allows us to schedule and reason about correctness. So thank you. I hope this was a good introduction to the architecture. I want to thank you for taking the time to spend with us today.